Well, with this, ladies and gentlemen, it is now time to move on to our next keynote, which is XAI, Explainable AI Everywhere being the topic. We're now joined by Dr. Peter Leong, AI Specialist, Singapore Polytech. Well, Dr. Leong is an AI specialist and a senior lecturer with the School of Computing, Singapore Polytechnic, where he teaches data science and artificial intelligence. Currently, he's also a consultant in the DSAC, where he works on the industry projects in data science and AI. With this, I'd now like to welcome on your stage and screen Dr. Peter Leong from Polytechnic. Thank you so much, Dr. Peter Leong, for joining us today. With this, I humbly invite you on the stage and screen.
Thanks for the welcome. Right, let me just share my screen.
Sure.
Right. Okay, welcome and good morning or good evening or good afternoon, depending on where you're dialing in from. So my name is Dr. Peter Leong, and I'm an AI specialist with the Singapore Polytechnic. And my topic today is on explainable AI, which is a very exciting area, and I think quite crucial for the further development of AI. So the title, Sci-Fi, is a play on the word Wi-Fi, because I hope to see explainable AI literally everywhere, as much as we see Wi-Fi now. So the outline of my talk this morning will be on the following topics. So first of all, I will be talking about what exactly is explainable AI. Many of you would have said that AI is artificial intelligence already, so why do we need to explain it? So I'll talk a little bit about what's meant by XAI or explainable AI. Then next, I will talk about how it is actually implemented, some of the different approaches that people are using to implement explainable AI. And then I'm going to talk a little bit about why I believe that explainable AI is quite crucial for the development of AI moving forward. And finally, a simple checklist and references for you to think about explainable AI moving forward. So a little bit of an intro about where I'm from. This is my home institution, which is the Singapore Polytechnic. So it is actually the first polytechnic set up in Singapore, and it is still the only polytechnic with the word Singapore attached to it. So it is, we pride ourselves as being the first polytechnic because we want to have this pioneering spirit. So in my school, we were the first to actually launch a new program of academic courses in the area of AI. So the two courses, one is for our day students, which is the Diploma in Applied AI and Analytics. It's a full-time course for our day students. And there's also a part-time course called the Specialist Diploma in Data Science and AI, which is for our adult students or part-time students. And these two courses were actually the first of their kind to be launched in Singapore and probably in the Southeast Asian region as well. So if you have any business in Singapore and you're looking for talent to actually help you to implement AI in your companies, do contact me or our institutions because we love to work with you. So let's move on into the topic itself. First topic is what is explainable AI? And I think for this question, we have to first understand a key component in modern AI, which is machine learning. What is machine learning? So the common understanding of machine learning is actually it is a set of algorithms or methods that computers use to make predictions. So it actually learns the patterns from the data itself, and using the patterns that it recognizes from the data, it's able to make predictions of various sorts. For example, it's able to predict the price of a house, or whether a student will be admitted into a university, or whether a patient with certain set of symptoms has COVID, right? So what's very interesting and novel about machine learning, which is actually the bulk of modern AI today, is that it's able to learn this without human beings actually teaching the computer to do it. So it's actually learning it autonomously by itself from the pattern itself. And this is really helpful when there are no human experts available to actually tell you more about the subject. For example, one of the things that hit us all is actually COVID-19, and COVID-19 being a new disease, actually there's no human expert around who's able to tell you what are the things that you should spot in the data itself, or the symptom data that you have. So actually, this has actually machine learning has been quite instrumental in our fight against COVID-19. So this is actually the machine learning, but what is explainable AI in the context of this? So this is actually a diagram taken from DARPA. And DARPA actually, which is the US military program for research. They actually have a special program for explainable AI because they also believe that it is actually quite crucial for many mission critical applications of AI in the Air Force. So first of all, the current state of AI today is what I mentioned just now, machine learning, right? So we are able, from the training data, by running it through a machine learning process, you're able to learn the model or the simulation that allows you to predict the results, right? So this the learn function of the model that's built from the data itself is able to make predictions for you, and as a user, you can make use of these predictions. For example, should you be taking this action? What do you expect to happen if you have a certain set of data? Are you predicted to succeed? Are you predicted to fail? But there are some things that are still missing from that information. And that's, for example, when it makes a prediction, actually, most modern prediction algorithms, they are only able to tell you the result. But many algorithms are actually what we call black box algorithms. They actually tell you the result or the prediction, but it's not able to actually tell you whether or not how that particular prediction is made, or why that particular prediction is being made by the algorithm itself, which is actually the topic of XAI, or explainable AI. So what explainable AI adds to this machine learning process is that instead of just being able to tell you what the predictions are, for example, whether or not a particular data is can be trusted, is it malicious data, or it is actually from a benign source, right? So whether it can be trusted or not, or is a dangerous piece of information. Explainable AI adds an additional layer where it actually has what we call an explainable model, and through an interface with the user is able to explain to the user why that particular prediction was made. So this is actually the additional thing that explainable AI actually adds to the equation. So traditional machine learning process has been very good. I mean, we started off the modern AI machine learning era with only maybe 70% accuracy, and sometimes 80% accuracy. But with the latest deep learning techniques, actually the accuracy goes up to very high, right? It can be 99.5% accuracy to predict whether a particular digit or a particular image belongs to a particular category. You can have very, very high accuracy with some of the modern techniques, but many of these models in deep learning, they are actually what we call black box models. They can give you that very high accuracy, but when you try to take a look under the hood to try to see how that decision was actually made, in other words, why did it decide to make that particular prediction? Actually, most of the modern algorithms are not able to do that. So this is why explainable AI is needed, because it helps you to look under the hood and understand why that particular prediction was made, why the particular prediction decided it was the negative case. It will tell you when you can succeed and when you can fail. Okay, and it helps people to achieve one important thing, which is actually to be able to trust the result from the explainable AI algorithm a little bit more. This is actually something which I feel is very important, and one of the key reasons why explainable AI would grow in the future. So the notion for explainable AI, as the name implies, is that instead of just having the predictions, it also has the explanation why a particular prediction was made by the algorithm. Now, how is actually explainable AI implemented? There are several different approaches to it, okay? And this actually comes from a book by Christoph Moner, which I will give you the reference later. And so there are two broad approaches. One approach is actually to look at what we call white box models that machine learning algorithms which generate models that are inherently interpretable, right? Some of these algorithms are actually tried and tested algorithms that are still in use in many industry applications. For example, regression algorithms, both linear and logistic regressions. They have parameters attached to them. They are basically parametric methods, and those weights or parameters tell us how important is a particular feature or attribute in making those decisions. So those parameters allow us to understand how that particular decision was being made by the model, because they help us to, these are what we call interpretable models. They are white box models. They can see what's happening under the hood by looking at the parameter values. Another group of algorithms that actually have this important feature of being interpretable are what we call decision trees. There are more than 100 different types of decision tree algorithms. They vary in the way they operate or how they measure impurity, but they have one fundamental feature, and that's actually it will generate a tree of different if then else rules, where it actually automatically decides the most important rule to be at the root of the tree. So decision tree algorithms are useful for interpretation or explanation, because the most important rule or the most important attribute will always occur at the beginning of the tree or the root of the tree. So these algorithms, they're helpful for you. But these algorithms, in terms of accuracy, they may not be as accurate as some of the state-of-the-art algorithms like deep neural networks or ensemble methods like random forest that we have. So actually, so they are interpretable, but unfortunately, they do not give you very high accuracy for many groups of data, because they are not able to cater for complex relationships. Now, one type of algorithm that actually comes from this is what we call a random forest, which is actually instead of having just one tree, you have multiple decision trees. But random forest algorithms are actually, although they give you high accuracy, they are actually belonging to the group of algorithms that are actually black box method, because you can no longer just, it builds you an ensemble of maybe 100 trees, and for one tree, maybe the most important parameter is A, but for another tree, the most important parameter may be decided to be B. So you don't have a global picture of how that decision was actually made by the model. So there's another group of methods called the model agnostic methods, and these methods actually are commonly being pushed now for use, because they are able to combine the results from black box models, which have very high accuracy. Okay, for example, the random forest and the deep learning neural networks I mentioned about. And there are two approaches to do this. Okay, so model agnostic methods allow you to build a model using your traditional non-XAI methods, but they build an interpretable model over and on top of the results from the original black box model. So one of this is actually what we call the global surrogate method. So these are some of the, there are two main types of model agnostic methods. One that looks at the overall picture of how those decisions was made. So it looks at the entire data set and builds a model to interpret the entire data set. So that's why they are called global methods. So one of it is actually the global surrogate method. And the other two are actually what we call local methods, where we don't look at the entire data set, but we look at how decisions are actually being made at certain combinations of data within the data set itself. Okay, so that's why they don't look at the entire data set, but they look at individuals. So these two very common methods called line and shape are actually local methods. So if you look at the IBM Explainable AI Framework, you will find that they have a slightly different way. Instead of dividing into interpretable models, they looked at it, okay, is your explainable method actually focusing on the data, or are you focusing on the model itself? So, so there are two different ways to look at it. So, and if you are looking at the model itself, is your model actually looking at the data from, as I mentioned just now, right? Either a global agnostic method, or is a local one that looks at only a particular part of the data. So you can see that actually the line and shape, they belong to the local explanations of this category. But there are other methods as well. So the IBM AI Explainability Framework is a very good one. It's actually quite well researched. So that's actually one of the references that I will also be referring to later on as well. So let's take a look at line and shape, because these are two local methods and they are quite easy to understand. They form the basis of many of the more sophisticated methods. So how line works, okay, and this is actually by a paper by Ribeiro Marco, okay, it's called the Why Should I Trust You paper, and it came out in 2016, not too long ago. And this is a local model agnostic method. So you build your model using the maybe a black box method like a deep neural network or even a random forest, and then you apply the line method over the original data, the input data, and the predictions made by your black box models. So it doesn't need to, it's called model agnostic because it doesn't really need to know what is the algorithm you use to train the model. So it can work with random forests, it can work with deep neural networks. It doesn't depend on the model itself, right? So how, let's say I'm trying to examine how the decision was being made in this region of data. Okay, so the big plus here with this region of data, and what line actually does is that it tries to make interpretation. The overall global picture is actually very complex. So we have two regions, okay, the pink region and the blue region, and the overall decision surface is actually very, very non-linear. This very complicated curve here, right? But where this particular data point exists, actually that particular boundary is quite linear, actually quite straight line here. So this is actually what line depends on, right? So there are, even though the overall global picture is very non-linear, but there are actually regions where we can approximate the relationship with a straight line. So what line does is that it takes the original data and then it basically perturbs or makes small changes to the data to see what is the result that will be generated by the original model, right? So it makes some perturbations to the original data, and you can see that some of the original data being shifted slightly here with all the small pluses here, and some of the original data being shifted on the other side of the decision boundary where they generate circles. And by perturbing the data this way, we can actually use the algorithm to basically generate a local region or local decision boundary right here where the dotted line is showing. So line actually gives you a series of local decision services, okay, that try to approximate the overall picture. So at least for this particular data point over here, you can understand which were the most important factors that were being used to actually decide on whether it should be a circle or it should be a red cross, or whether it belongs to the orange, the pink region or the blue region. But over at somewhere else, okay, maybe another region, then the line will be different. So it's a local method. It only applies to a particular data point that you have in the entire data set. So you can see below on the right hand side here, basically it says that, okay, to decide that it is the 5 most important factors for this particular class where the positive point is actually this few features: ACT, LIM, WLK, LIM, and then also the K642, sum 42, and then H, right? These are the important factors at this region of the data. Okay, so LIME was the very first local model agnostic method that came out. The second one, which is called SHAPE, actually is an improvement over LIME. Actually was introduced about 1 year later by another group of researchers. And what they did was that they actually considered different combinations of the metrics or the features rather than just perturbing the data itself, right? So they actually have different subsets they will look at, but the idea is still very similar. They want to basically find local regions and see which are the most important features in certain local regions of the data. This is also a model agnostic method, so it can work with deep neural networks. It can also work with an ensemble method. So it doesn't depend on the type of modeling algorithm you use. It just looks at the original data and then the predictions that were made, and then it actually applies this over and on top of the predictions and the original data. So you can see the output is very similar to the line. It's a little bit more complicated here for SHAPE, okay, but the idea is the same. Okay, so the more important features will have a larger feature importance value attached to them, whereas the not so important features, they will have a lower value. So what we want to look out for is that at this particular part of the data, which are the most important features. And you can see that actually picks up the ACT limb again, right? And the other one was the K40, no, there's some of the other one like the WKL limb as well. So it actually gives you those values that indicates this is a very important feature for making the decision at this particular part of the data, where that cross is was just now. So this is some methods, but there are other methods as well. So if you are interested, I highly recommend the references that I'll come to later. But why is it that we want to consider explainable AI? Okay, why is it important over and on top of traditional machine learning? And the Department of Defense, okay, actually take a look at this, okay, because it helps them to understand why. And there are many mission critical applications, for example, in security, finance and legal, and even transportation, where it is not good enough to merely have the prediction. You need to understand how that prediction was being made so that you can actually engender some trust amongst the users. So for example, right, it's a simple example. Let's say my model predicts that a particular student who has applied to my university did not manage to get in. His application failed. Now the student, of course, would be interested to find out not just that he failed to get in, but why exactly was he not chosen or admitted into the course. The why is very important for users to be able to trust the results of the algorithms. So this is expanded. So trust, okay, is the underlying idea. Okay, trust on the left here. To build user trust, not only we want to have very highly accurate results, but we also need to also be able to explain or indicate how that decision or why that particular decision was being made by the model. So to engender trust, we need to have explainable models, not just high accuracy models. Secondly, fairness. So by understanding why a particular decision was made, we can detect whether or not the model is making any biases, whether or not certain parts of the data that should be protected is being used, whether the model is robust. Does a small change in the data actually affect the result a lot? And finally, we can understand what we call causality. Just besides just correlation, is there some cause and result effect that we can see in the data itself? So this is actually some of the reasons why. So in terms of the checklist, and I think I'm running out of time, it's important to consider who is going to be looking at the explanations, right? So because the different levels of explanation depends on whether you have a global model or local model, depends on the audience for your explanation. So these are some of the references that I mentioned just now. Christoph books, which is a free book, is a very good reference model, and many of the things that I presented just now actually taken from this book. The other one which you should take a look at is the IBM 360 Explainability Framework, and it's actually available as a tool from IBM as part of their research from IBM Research, and they have a paper for the methods there as well. So thank you very much, and I think this is my last slide. As I mentioned just now, anyone who's interested to work with my students in Singapore Poly, do contact me, and that's my contact.
Right. Thank you so much, Dr. Peter Leong, for joining us today at our show. It was a pleasure hosting you today. Thank you once again.